Hi, everyone, and welcome back to the Smart Tea podcast, where we talk about the lives of scientists and innovators who shape the world. I'm Aarati.
And I'm her mom, Jyoti.
And welcome back, everyone, to our December extravaganza on thermodynamics.
Yes, we are doing 3 scientists in a row where the work of one physicist is building the work of the next physicist and so on and so forth until we are doing 3 in a row.
Yeah. So if you didn't listen to the previous episode on Sadi Carnot, I highly recommend you go back and listen to that first and then come back to this episode, because today we're going to be talking about another physicist who built on the work that Sadi did.
Yes, I'm so excited to listen to this. And I remember that Sadi Carnot was in France, but then now we are moving over to a scientist in Germany.
Yes.
And how many years later is this work?
Only a few years, only a couple of years later. So,
Oh, that's pretty good. Okay.
yeah, like maybe, I think Sadi Carnot died in 1832, I think, if I remember. And then his work was translated 2 years later. And then
Okay.
very shortly after that, it made its way into the hands of the scientists today.
Perfect.
So we did mention in the end of the last episode, and of course, if you've looked at the title of this episode already, you know that we're going to be talking about Rudolf Clausius,
Yes.
who is credited with laying down the first 2 laws of thermodynamics.
Whoa. So we started with Sadi Carnot, the father of thermodynamics, and then now we are doing Rudolf Clausius, who laid down the first 2 laws of thermodynamics. That is pretty awesome stuff we are doing here. This is fun.
Yeah. Sadi Carnot kind of laid down the basic fundamentals of thinking about how heat and work are kind of related to each other. And now Rudolf Clausius comes in and really defines a lot of these laws and how things are working. So he's done a lot. This episode is going to be very physics heavy, so prepare yourself.
Ooh, okay.
Yes.
Okay.
But before we get into that, first a little bit about his life and how he got into thermodynamics to begin with.
Yes.
So Rudolf Julius Emanuel Clausius.
Whew, what a mouthful.
Yeah. Yeah. Was born on January 2nd, 1822 in Koslin, Poland, in the province of Pomerania, Prussia. He was the youngest of, get ready, 18 children.
Wow, from the same mom?
Don't know about the same mom, but
Oh, wow.
That's a good question.
Yes.
If so,
yes.
that poor lady.
Oh my goodness. She spent most of her life childbearing then, and child rearing, of course.
Yeah. His father, because, of course, during these times, we know more about the father than we do about the mother. Always.
Yes.
That's kind of how it goes.
Yes.
His father was a Protestant pastor and had founded a small school where he served as principal.
Okay.
So Rudolf was educated early on in this school. In 1838, when he was about 16, he continued his education at the Stettin Gymnasium, and gymnasium is the word that they were using for high school.
Oh, interesting. Okay.
Yeah.
I wonder if schools used to be more sports heavy in those days. Maybe that's why they were called gymnasium. It was more focused on physical development.
I don't know. When I was reading his story, maybe it's a German specific thing. I don't know. Somebody in the audience let us know. But when I was reading his story specifically, there was a lot of gymnasiums involved. But it seemed like it was another word for high school. And I think I looked it up also, and it said it was an antiquated term for high school. So
for high school. Okay.
Yeah. I don't know. Maybe it was the word and then it fell out of favor, or it's a German thing. Not 100% sure, but
okay.
So he goes to high school, and then 2 years later, in 1840, he enrolled in the University of Berlin. He was initially a bit torn as to what he wanted to study. He was initially drawn to history, but ultimately wound up completing a degree in math and physics. He graduated in 4 years, and then he spent 1 year teaching advanced math and physics at the Friedrich Werder Gymnasium. So again, there's that
Once again, gymnasium, and it's probably high school. So now he's a high school teacher.
So he then went on to the University of Halle to study for his PhD in physics.
Okay.
Here, his dissertation aimed to explain, among other things, why the sky was blue and why we see different colors at sunrise and sunset.
Oh, the fractionation of light.
Yes.
Nice.
So, in his dissertation, he proposed that it was because of the refraction and reflection of light, which
Okay.
ultimately turned out to be incorrect. Now we know it's due to the scattering of light.
Okay.
So, when a light wave hits a particle of something in the air,
Hmm.
it's deflected in a bunch of different directions.
Yes. It splinters into its component waves.
Yeah. So he turned out to be incorrect about that. But the math that he used in his dissertation was novel and pushed the boundaries of mathematics. And so it was
Hmm.
still very impressive. After graduating, he returned to the Frederick Werder Gymnasium and continued to
Mhm.
teach there for the next 6 years.
Wow. Must have liked it.
I think so, yeah.
Mhm.
I was also thinking about how these high school students had like PhD level math and physics people teaching them. I
Yes.
I feel like that's amazing, and I think it was very common for the time. I've heard this in other stories. I think Santiago Ramon y Cajal was also like that, where
Yes.
people who had PhDs in biology went and taught high schoolers.
Yes. To put the education of the young minds into competent hands.
Yes, exactly.
And it was obviously a noble profession. It's still a noble profession, but it's not valued enough by society these days in terms
Yeah.
of payment and all that, which is very sad actually.
Yeah, and I don't want to get too political, but I saw recently that there was like a proposal or something for certain college degrees to be like devalued basically. So like if you
Oh,
got a PhD in education or a degree in nursing or a degree in physical therapy or something, it would no longer be called a doctorate. It would no longer have that same
oh,
status.
oh no.
Yeah.
Oh,
And
that is
people were
so
pointing
sad.
out that, a lot of these degrees are actually degrees that are pursued by women. And so it was just another way to devalue like teaching,
Oh,
nursing, all
oh
of these
no.
kind of professions.
This is
Yeah,
so sad. But we
I
are
know.
really going backwards in a very big way.
I know. It's ridiculous. And,
Yes,
we know people like that. We know people who have degrees in physical therapy and in,
absolutely.
nursing and stuff. And that's hard work. Like
Yes,
that's,
yes.
oh my
They
God,
have
I couldn't
killed
do it.
themselves and got into deep student loans for getting these degrees, and now it's like devalued, which obviously means that now their pay will be comparatively lower.
Yeah.
That
And
is a
even
very sad.
education, like the amount of work these teachers put in to making classes, educational and fun and engaging is just
Yes,
incredible. And
absolutely.
you cannot devalue that.
You cannot devalue that. No, we'll pay for this as a society down the line because
Hmm.
basically you're not investing in the growth of young minds.
Yeah.
So we are going to see a lack of analytical thinking. And so then young people then will tend to kind of follow the drum. They'll find somebody who they believe in and just go by what one person says. So, sort of like a cult mentality. If so and so says it, then I'm going to believe it and move on
Yeah. The
from there.
critical thinking is lost.
Correct. Very
Yeah.
sad, actually.
And education also just exposes you to so many different facets of the world, so many different types of people. So there's that's being
Yes.
lost as well. So,
Yes. Very sad. And then you become insular when you don't understand other cultures, when you don't understand what's happening with other people in other parts of the world. You
mhm.
become extremely insular. You become more judgmental. You become less tolerant.
Yeah.
So it's a shame and it's a big loss for society.
Yeah. So let's go back to happier times in the
Yes,
1800s.
where Clausius, with his PhD degree, is teaching young high schoolers about math and physics and all that good stuff. Okay,
Yes. And then on the side, he continues to study physics and math himself.
keeping abreast of what's going on in that field.
Hmm. In 1849, he comes across a paper written by his contemporary, William Thomson, who we've talked about before, aka Lord Kelvin,
That's right.
about the theories of heat. And in this paper, William Thomson referenced Sadi Carnot's work on how heat can be turned into work and vice versa.
Okay.
So Rudolf gets interested in this. He starts digging
Mm-hmm.
deeper into Sadi Carnot's work. And he determined that Sadi had some very good points.
Mm-hmm.
But there was one glaring problem, and we did talk about this a little bit last episode. The problem is that Sadi wasn't sure exactly what heat was.
Yes. Okay.
So there were two hypotheses at the time. Sadi Carnot, Emile Clapeyron, who was the guy who translated Sadi's work from French into
Yes.
English.
Mm-hmm.
So he, Sadi, and a majority of other physicists actually believed that heat consisted of an invisible weightless fluid called caloric.
Oh, correct.
Mm-hmm. And that flowed from hotter objects to colder ones, the same way that water flows from higher levels to lower levels.
Okay.
Because of this, Sadi believed that no heat, or in other words, none of this caloric substance, was lost in his theoretical engine. Instead, he thought that heat was this substance that was doing the work as it
Yes.
flowed through the system.
Got it. Okay.
But Rudolf took particular issue with this statement that no heat is lost. He fell into a smaller camp of physicists who believed that heat was the transfer of kinetic energy of particles in one substance to another.
Yes. Getting closer to the truth.
Mm-hmm. And because of this, he believed that in Sadi's machine, and, quote, in all cases where work is produced by heat, a quantity of heat proportional to the work being done is consumed.
Yes.
And inversely, by the expenditure of a like quantity of work, the same amount of heat may be produced. End quote.
Okay. So basically, it's a back and forth. It's a reversible situation. Heat can become work and work can become heat.
Yes.
In an equivalent way, sort of.
Yes. And so he's the one who's really introducing this idea of transformation, that heat is not a fluid that is doing the work, but rather it's transforming into the work.
Yeah. So heat itself becomes work. Work itself becomes heat. Yeah.
Yes. And so they're like two sides of the same coin kind of
It's
thing.
like a water and ice, basically. Water becomes ice. Ice can become water, that kind of thing. So same thing. Heat can become work. Work can become heat. It's not like there is a substance there that is now flowing and doing something and creating work like that. It's not, they are not two separate entities.
Yes. And that's why he took issue with Sadi Carnot saying that no heat is lost. He was like, yeah, heat is lost because it's being transformed
it's become
into
work now. Yes.
Yeah, so you did lose heat.
Yeah. The piston moving was work and that much heat is lost.
Yes. But it's important to note that Rudolf wasn't the first ever physicist to say this. And in fact, he relied heavily on experiments of an English physicist, James Prescott Joule, who proved experimentally that heat was in fact a form of energy and not an invisible fluid. And of course, Joule is the unit of energy that we now know and use in physics.
That's right. These are like the classic names that are we are using even today. Ampere, Joule, Kelvin. All these are the units of major things like work and heat and all of that.
And they're all running around this thermodynamics problem at the same time.
At the same time, tackling it all. It's a nice thing to think about where they are all sharing their knowledge with each other equally so that they all get to the right solution and to the right conclusions faster, serving mankind that way, rather than saying, this is my idea and I'm going to hold it and I'm not going to share. It's very cute to see that.
No, they would absolutely, they publish it, then everybody would look at it, poke holes in it, they would refine it, so huge amount of work.
And that's how
right now.
We have the thermodynamics as it stands today is thanks to all these people and their total focus on understanding the subject rather than self-glory.
But the other actually interesting tidbit I found was that Sadi Carnot actually later in his life came around to the same conclusion that heat was kinetic energy between molecules and it wasn't an invisible fluid. But he died before these thoughts could be formally published.
Or
And
maybe they got destroyed by that stupid cholera that he got.
I think a lot of it did, but there were some private notes that somehow survived, and those private notes were only made public in 1890, which
Okay.
is years after all of this is taking place. Rudolf
Yes.
Clausius and James Joule's experiments and everything is
Yes.
happening like 50 years earlier. And then
Yes.
in 1890, 50 years later, people are like, oh, Sadi Carnot actually also
Said
had the same,
this.
came around to
Yeah.
the same
Yeah. That
conclusion at
one
some
piece
point.
of paper that survived that the destruction of all his personal effects shows that he was on the right track at the end.
Yeah, somebody found it tucked away, like his brother's son or something must have like opened a book and said, "Hey, Uncle
Here he
Sadi
says
had
that
this."
already.
Yeah. Okay, so back to Rudolf. So in 1850, Rudolf published a paper called On the Motive Power of Heat, which
Hmm.
is largely credited with being the first complete version of the first law of thermodynamics ever written.
Hmm. Wow.
In this law, he introduced some new terminology, interior work and interior heat,
Okay.
which today we basically just call internal energy.
Okay.
And he gave this the symbol U. The equation that he wrote down in his paper was delta U equals Q, which stands for heat,
Hmm.
minus W, which stands for work. So, in other words, the change in the internal energy is equal to the amount of heat you put into the system minus the amount of work that you get out.
Yes. Okay.
This was a breakthrough in physics research and
Hmm.
skyrocketed Rudolph's career. Because of it, he was offered an academic position at the Royal Artillery and Engineering School in Berlin and became a docent at the University of Berlin.
Oh, nice.
However, I was also watching a video on YouTube from the
Mm-hmm.
channel Kathy Loves Physics.
Hmm.
She's great, by the way. If anyone is interested in anything related to physics and history of physics, especially, go check her out. She really lays it down a lot of like interesting tidbits, and she really knows what she's talking about when she's talking about all these
Nice.
equations and, things like that. But one thing I picked up from her channel was she was saying that Rudolph's ideas about the relationship between heat and work were
Hmm.
very similar to and definitely inspired by many of his contemporaries,
Hmm.
including William Thomson, William Rankine, and Hermann Helmholtz.
Okay.
And when they read Rudolf Clausius's papers on the first law of thermodynamics,
Yeah.
they essentially were like, he's copying us. This is our
Hmm.
work, and he's just rephrasing it or,
Yes.
relying heavily on our work to draw the same conclusions that we are drawing.
So basically, Rudolph presented the same ideas in a very refined and concise way so that it could kind of be put into an equation rather than just talking about it and trying to theorize about it. He came up with an equation that explained it.
Yeah. So that's what we give him credit for today. It's like a lot of people were circling the point here
Yes.
with like William Thomson, William Rankine, all these people, they're doing experiments that are kind of leading to the same conclusion. And Rudolf Clausius is taking all of this and here it is. Here's the rule in a very succinct mathematical way that
Yes.
is supported by all of your information, all of
That's
your,
right.
your experiments on heat, your experiments on energy, your experiments on work. All of this is supporting this one universal truth. Here's the
Yes.
truth. That's
Yeah.
the first law of thermodynamics.
Got it.
And
Okay.
everyone's like, yeah, that's basically what we're saying. And he's like, yeah, but I
That's
said
what
it.
I said.
Yeah. And he's
Isn't
like,
that
no,
what I
I
just
said,
said?
yeah,
Yes. Yeah.
yeah,
I can see that. Okay.
yeah. So because of this, because they kind of were like, you're copying us, whenever Clausius tried to publish a paper over the next few years, they would hound the editors of the journals to complain about how Clausius had copied them or gotten things wrong.
Hmm.
But as we were just saying, one science historian wrote, quote, there is no doubt that Clausius, with his paper, created classical thermodynamics. All preceding, except Carnot's, is of small moment, end quote.
Oh, wow. Okay. Okay.
Yeah.
Hmm.
So it's like everyone else is supporting Clausius's main
Thought.
thought.
He's able to bring all these multiple thought streams of multiple people together to create one very clean equation that becomes the first law of thermodynamics.
Yes. So Rudolf continues to shine and continues to publish papers on heat. He also continues to look at Carnot's cycle, and his next conundrum that he was like, something's up here.
Yeah, something is not quite right kind of thing.
Yeah. Was that he knew Carnot's cycle consisted of reversible steps, where you could do the 4 steps in one way and get heat, or do them reverse and get work.
Yeah, I remember 1 and 3. Step 3 is the inverse of step 1. Step 4 is the inverse of step 2.
Yes.
Yeah, in Carnot's cycle.
Yeah. So he was like, yeah, great. Perfect. But he also believed that heat always flowed from the hotter object to the colder one and never reverse. So mathematically, if you're only working with heat, this reversibility doesn't make sense unless heat can flow from a cold object to a hot object.
To the hot. Yeah.
Yeah. Which even Carnot knew it didn't do. So
that's right.
He's like, mathematically, if you're only looking at math, like if you're looking at the physics, it makes sense. But if you're looking at just mathematically, how do you reconcile this with numbers?
Yeah.
It doesn't make sense unless you can have heat flowing from cold objects to hot objects, which we know it doesn't do. So how
it doesn't do.
Yeah.
Yes.
So how do you define this mathematically in a way that makes sense?
How do you reconcile it? Yes.
Yeah. How do you reconcile the physics with the math?
Correct.
So in 1954, Rudolf published his 4th paper on heat, in which he laid out a term called the equivalence value, which was equal to heat divided by temperature. So now, if temperature is held constant, if heat goes in, you get a positive value.
Okay.
And if you reverse it, when heat comes out, you get a negative value.
Yeah.
So let's say, for example, just 100 in, 100 out. So when you add these two values together, you do 100 heats in plus negative 100 to take the heat out.
Take the heat out.
Yeah, you get a net equivalence value of 0.
Correct.
So in this case, the system is perfectly reversible. That's Carnot's cycle. There's no heat loss due to friction or leaks or anything like that.
Correct.
But remember, again, Sadi's engine was an ideal.
Yes, and it was only theoretical.
Yes. So in real life, most systems are not perfectly reversible.
Yes.
So if you imagine you put heat into the system, let's say 100 again, now the system loses energy due to heat leaking or friction. So when you reverse the system, you get out less heat than you put in.
Yes.
So let's say you get back only 80% because the other 20% was lost.
Yeah, you dissipated it somehow. Yeah, wastage.
Yeah. So now you have 100 heat in plus negative 80 heat out.
Yeah.
Which gives you a net equivalence value of 20.
Yes.
And this is a bigger number than 0, obviously. Yeah. But could you ever get a net equivalence value that was less than 0? So could you ever put in 100% heat and get back out 120%?
120.
Yeah.
Yes.
So Rudolf was thinking about this and he was like, the only way for that to ever happen, if the system is a closed system and you're not putting in more heat somehow to get that 20% extra back out.
That's right.
Yeah, so it's a closed system. The only way to do that would be if somewhere in the system, the heat was flowing from a lower temperature to a higher one, which we know is impossible. In a natural system, that doesn't happen.
Okay.
So Rudolf stated that in a complete cycle, if it's reversible, you will always get an equivalence value that is greater or equal to 0.
Okay.
You can never get a negative
you can't
equivalence
get a negative
value.
Yeah, because
so
heat doesn't flow the opposite direction. It doesn't go from cold to hot.
So this was another big breakthrough. In 1855, he was appointed to the chair of mathematical physics at the Polytechnicum in Zurich. and appointed as a professor at the University of Zurich. So his work is really capturing the attention of a huge
Yeah,
audience.
he's making waves there.
And at the University of Zurich, he's able to reach an even wider audience of physicists and push forward his ideas because the University of Zurich was, and probably still is, known
Well
for,
known. Yeah,
yeah,
it's a better platform. It's a more widely regarded platform, and so he has a bigger megaphone basically now to push his ideas out.
yes. Around this time, he also got married to a woman named Adelheid Rimpam,
Hmm.
and together they started a family.
Hmm.
So things are going pretty well.
Pretty well for him. Yeah.
Hi everyone, Aarati here. I hope you're enjoying the podcast. If so, and you wish someone would tell your science story, I founded a science communications company called SciComm, that's SYKOM, that can help. SciComm blends creativity with scientific accuracy to create all types of science communications content, including explainer videos, slide presentations, science writing, and more. We work with academic researchers, tech companies, nonprofits, or really any scientist to help simplify your science. Check us out at SciCommer.com. That's SYKOMMER.com. Okay, back to the story. So then 8 years later, in 1862, Rudolf published another paper on his equivalence values that asked the question, now what if the system's not reversible? What if it
Okay.
just went in one direction and stopped?
Yes.
So if you're putting in heat
Yeah.
and you're not reversing the system to get the heat back out, then the heat just stays in the system and increases the temperature until the object reaches a new internal state.
That's right. Okay.
So what is changing then? What's happening to the molecules in that system
Yes. Yes.
as it heats up?
Correct. Correct.
So at first, when Rudolf looked at only gases, he
Hmm.
thought when you increase the temperature of a gas, it expands, right? We have
Hmm.
PV equals nRT.
Yeah.
So pressure stays constant, then volume increases when temperature increases.
Correct.
And so that must mean that the gas molecules must be getting further apart from each other
Yeah.
for volume to be increasing.
Yes.
But then he realized that doesn't work for everything. So, for example, some substances like water, if you have liquid water and then it becomes solid ice, when the molecules freeze in this very structured lattice shape, they're kind of far away. But when
Yeah.
the temperature increases and the ice melts, the water molecules actually get closer together.
That's right. That's right. Because they are not bound in a very defined lattice structure. So
Yes.
they are now free flowing. They can use less space to sit in a little bowl. Yeah. Yeah.
Yeah.
Got it.
And then if you heat it up even more into steam, then the molecules get further apart.
Correct. It can go back and forth basically. Yeah. When it's cold, it's using more space. Then it becomes liquid. It uses less space. Now it's become gas, which means even more heat than liquid. And now it is using more space. So the coldest is using more space and the hottest is using more space. The intermediate where it's water and it's in between the coldest and the hottest, it's using less space than either of those.
Yes, exactly. And so it's like I can't write one just universal law that says when you increase temperature, the molecules are going to get further apart or
Yeah.
volume is going to increase.
Yeah.
That's not true. So instead, he concluded that when the temperature in the system increased, the molecules became more disorderly.
Yeah. He's coming up with the right points now. Yes.
Mm-hmm. So in the real world, when we have equivalence values that are always positive, that means that molecules are always getting more disorderly.
Yes. Are we headed towards entropy?
Yes, we are.
Ooh,
Yes, we are.
yes.
We're getting
Okay.
there. So in ideal cases, you can have an equivalence value of 0, which means the molecule's orderliness stays the same.
Yes.
But you can never have a closed system where the orderliness of molecules actually increases
Yes.
because you can never have an equivalence value that is less than zero.
Yeah. Yeah. Yeah.
So Rudolf spends the next couple of years refining his theories. And 3 years later, in 1865, he publishes On Different Forms of the Fundamental Equations of the Mechanical Theory
Mm.
of Heat, which officially renames the equivalence value into entropy.
Ah,
Yeah.
yes. So that initial thought that he had, there's an equivalence value. When he
Mm-hmm.
said that, he's really thinking about the heat going in, causing agitation in the molecules.
Mm-hmm.
It's like when I think of entropy, I always think of a 3-year-old having a sugar high, and yeah,
Just going crazy.
yeah, because you can give a system a lot of heat, and the molecules inside start to be agitated and bounce off the walls.
Mm-hmm.
And that, for me, when I want to visualize entropy, I always think of young little kids getting a lot of sugar.
Yeah, you give them a lot of energy and now they're
Yeah, and now
going
they're
crazy.
bouncing. Yeah,
Yeah.
yeah. So it's really that for me. That's a very visual representation of entropy. That's what
Yes.
entropy is all about. You
That's
give them
exactly
heat.
what it is.
Instead of heat, you give them sugar. That's it. Yeah.
Yeah. Good one. Yeah, so his equivalence value is basically entropy. He renames it entropy. He gives it the letter S for some reason. No one knows why.
Hmm.
But the word entropy comes from the Greek word for transformation. And it is a
Uh-huh.
word that Rudolf intentionally chose because it was similar to the word energy.
Okay.
So he wanted people to link those two
Yes.
things.
He wanted it to be linked. Okay.
Yeah.
Yeah. He seems like a really smart guy. Yeah.
Yes. He's a smarty.
One more smarty.
One more
Good one.
smarty.
I like that.
Yes. This paper also officially lays out the first two laws of thermodynamics in a way that we recognize them today. The first law that he wrote is that, quote, the energy of the universe is constant.
Hmm.
And so, other ways that we've said that is like energy can neither be created nor destroyed. And so, that's again getting into that heat is transforming into work and vice versa. It's not,
Yes.
being destroyed, it's not being created.
Yeah. And you're not creating something new there. It's just heat becoming energy, energy becoming heat.
Yes,
You're not, you know, creating something different entirely.
exactly. And the second law that he wrote was the entropy of the universe tends to a maximum. In other words, entropy is always increasing.
Always, yeah. It's always the universe is going towards disorder,
Yes.
which we see even amongst people and
Yes,
societies.
always.
We
Always.
are all headed towards more and more disorder.
Yeah. We're all going crazy here.
It's built into us. We can't.
Yeah.
We can't do anything about it.
Yeah. Might as well just go along for the ride.
Might as well just go along with this disorder.
Yeah. Meanwhile, although he's thriving in Zurich, he
Hmm.
starts to miss Germany.
Oh,
Over the years, he had actually turned down offers from German universities like the Polytechnic University in Karlsruhe and the Polytechnic in Brunswick, because neither of them really offered the same scientific excellence and
ah,
opportunities or the ability to reach such
that
a
he
wide
was able to find
audience.
in Zurich. Okay.
Yes.
Hmm. Hmm.
But by 1867, when the University of Würzburg offered him a professorship, he
Mhm.
finally couldn't resist anymore. He deeply regretted leaving Zurich, but he was very happy to be going back to Germany at last.
Yeah, yeah. He's doing his best work in every place. So, yeah.
Hmm. This same year that he moved from Zurich back to Germany, in 1867, Rudolf Clausius wrote another paper on examining how temperature related to molecular movements. He proposed that molecules could not only move translationally, i.e., in a straight line,
Yeah.
but also vibrationally and rotationally as well.
Yes.
He also found that molecules move incredibly fast.
Mm.
So I didn't know this at all. It really blew my mind. So, for example, the air that is around you right now is made up of tons of different molecules. We have nitrogen,
Hmm.
oxygen, hydrogen. We have all these things.
Yeah.
At room temperature, according to Rudolf Clausius's equations, on average, each molecule is moving at 500 meters a second or over 1,100 miles per hour.
No way.
Isn't
Oh,
that
wow.
insane? They're moving so incredibly fast.
Yes.
But when Clausius proposed this, because he's like, all the math that I'm doing points to these numbers that are just
Yes.
incredibly high,
Yeah.
people were like, how is that even possible?
Impossible. Impossible. Yeah.
Because if molecules were really moving that fast, every time that, something happened in one part of the room, like if there was smoke or perfume or something in one part of the room, it would immediately fill the whole room. It would be everywhere
Dispersed
immediately.
very quickly. Yes.
Yeah, like instantaneously. And we know that that's not the case. We know it kind of diffuses really slowly throughout the whole room.
Yeah.
Rudolph was like, great question. I wonder why that is. And his answer was that even though the molecules are moving very fast, they aren't moving very far.
So they're just kind of dancing around in place.
Not dancing around in place, but there are billions of molecules in the air all moving in
Yeah.
random directions and bouncing off of each other.
Mm-hmm.
So if you spray perfume or add some smoke, into this room, these molecules join this like madly jostling crowd of molecules that are all
Yes.
bumping into each other randomly, changing direction like crazy. And
Yes.
so because of that, they're like expending a lot of energy to not move very far. And
Makes
so
sense.
it takes a
Yes.
long
Yeah.
time for
There
them
is
to actually
nowhere
get.
to go because there is so much, there are
Yeah.
so many molecules all over the place. It's like being caught in one of those really tight situations, like a stampede or like in a big hall where there are so many people and
Mm-hmm.
you can jump up and down all you want, but there's nowhere to go.
There's nowhere to go. Yeah.
Yes.
So you got to move slowly, even if you are on a sugar high and going nuts. And
Absolutely.
so Rudolph came up with a new term called the mean length of path, which is how far on average can a molecule move before its center of gravity comes into the sphere of action of another molecule.
Huh.
That is going to be important in our next episode. So put a pin in
So
that. Yeah.
that's the building block. Just like Carnot cycle was important for Clausius, same way this mean path length is going to be important for the next person we are going to do.
Exactly. Yeah. In 1869, Rudolf accepted a chair position at the University of Bonn in Prussia,
Mm.
which was a large northern German state. However, just when he's soaring high with his academic achievements, the Franco-Prussian War broke out. I'm not going to get too much into it. Their entire history, documentaries, that are dedicated
Talk
to the
about, yeah.
Franco-Prussian War and what
Hmm.
exactly happened and why. But just really briefly, 2 years earlier, Queen Isabella II of Spain was overthrown,
Okay.
and a man named Leopold of Hohenzollern, who was a relative of the King of Prussia, was
Mm.
chosen to succeed her.
Okay.
But France, which sat in the middle of Spain and Prussia, didn't like this because they already had tension with Prussia. And now, if Spain became a strong ally of Prussia through this succession, they would be surrounded, basically.
Yes. Yes.
So then one thing led to another. There was like some, sabotage and intentional misleading of people. And France ended up declaring war on Prussia.
Okay. So that causes the Franco-Prussian War. Hmm.
Yes. Rudolph was 48 by this time, and so he was too old to be in combat.
That's good.
Yeah. But Rudolph's brother wrote, quote, his burning patriotism did not permit him to stay idle at home during the War of 1870 to 71. He undertook the leadership of an ambulance corps, which he
Mm.
formed of Bonn students. At the great battles of Vionville and Gravelotte, he helped carry the wounded from battle and to lessen their suffering, end quote.
Oh, wow. What a noble guy.
Yeah. And even more noble is that I read that it didn't matter who was wounded, if it was a
Oh,
Prussian person or a French person. He just got them off
wow.
the battlefield and made sure that,
You're a human being and
yeah,
lessen the suffering of humanity. Wow,
yes,
he's a noble soul. Beautiful.
very much. During the battle, though, Rudolf was wounded in the leg, which left him with
Oh,
a painful disability that he suffered with for the rest of his life.
oh, that's sad.
But he did win the Iron Cross in 1871 for his
Okay.
bravery. His patriotism was tested again, this time more scientifically, when a Scottish mathematician and physician, Peter Guthrie Tait, wrote an extremely pro-British review of the thermodynamics work that was being done by other British physicists like William Thomson and James Maxwell.
Okay. So when you say pro-British, what you mean is that he was expounding on the accomplishments of the British scientists, the findings of the British
Mhm.
scientists, and basically saying, that's it, they are the best thing since sliced bread kind of thing. And then everybody else can go take a nap kind of thing.
Exactly. Yeah. He was
Okay.
like, look at all this
Okay.
fantastic work. It's brilliant.
Yes. Got it.
And Rudolph was like, hey, you British scientists are not only trying to take more credit than you should for some of your
Hmm.
theories, because like
Yeah.
us Germans did something too, but also you're misinterpreting, like when you do talk about my work,
Yeah.
you're misinterpreting my work and making it, seem like I got things wrong when you're the one who's getting things wrong, you know?
Got it. Got it. Uh-huh. Uh-huh.
So Rudolph wrote to James Maxwell because of this Tate person. Tate was
Hmm.
basically saying Maxwell is so wonderful. He wrote all this stuff about heat and work and energy, and contrast that with Rudolf Clausius, who has these other ideas about heat and work and energy.
Hmm.
And Rudolf
Hmm.
Clausius is totally wrong, and James Maxwell
Hmm.
is the best, and all of that. So
So Rudolph is directly approaching Maxwell and saying, cut this person out. Let's talk this out.
Rudolf is like, Tate has compared our work.
Hmm.
And actually, if you look at that direct comparison, you're wrong. Like James
Yeah.
Maxwell, you're wrong. This guy is thinking that I'm wrong, and he's saying that British people are great and British scientists are great. But
Right.
actually, you're the one, James Maxwell, who's wrong. And let me show you. And James Maxwell is like, oh, you're right. I am wrong, you know?
Oh, wow. Wow.
Yeah.
That's great minds, man.
Yeah.
Almost unheard of in today's world. The today's world, it's all about doubling down and sticking to your ideas no matter who proves them wrong. Wow. Wow.
Yeah.
Nice.
I almost got this impression of Tate being this like screaming, petulant little like
Yes.
child, and then
Troublemaker.
the two
Yeah.
parents are like,
Instigate.
"Shh,
Yeah.
we're
Yeah.
talking,"
Let's figure this out.
Yeah,
Yes.
the two level-headed adults are like, "Okay,
Yeah.
you know what? Actually, in all of that rambling, the child did make a good point.
Yes.
Like
We
let's
should
talk about
compare
that."
them and figure out who is right. And actually, the child got it wrong. This
Yeah.
is, you are right after all. Wow. Nice. Nice. So wise. So mature.
So James Maxwell fixed his misconceptions in the next edition
Hmm.
of his book.
Hmm.
But Tate continued to somehow misunderstand or completely ignore Rudolf Clausius's work, which ticked him off a lot. And so he spent a lot of time writing to publishers and magazines calling out Tate's errors.
Okay.
After this, the details of his life get a bit scarce.
Okay.
We know that he was spending a lot of time, like, calling out Tate's errors.
Mm-hmm.
In 1875, Rudolph's wife, Adelheid, sadly died, giving birth to their sixth child.
Oh, okay. Hmm.
So, because of this, Rudolph stepped back from his work to become the primary caregiver to his
Hmm.
children.
Wow. And this is, you said he was already like 40 something, 48 or something at this
48
point.
during the Franco-Prussian War.
Yeah, and
Yeah,
now he's older. He's probably closer to somewhere in the mid 50s
50s.
now.
Yeah, mid 50s now. He continued to teach, but he was no longer able to contribute new ideas on thermodynamics.
Hmm.
And after this, there actually wasn't much information about who Rudolph was as a person. So when you take away like his scientific achievements and try to just look about for information about Rudolf himself and his personality and like his hopes and dreams and stuff like that, we
Yeah.
actually don't know much about it. Some historians think that maybe it's because he was a bit more on the quiet side.
Mm-hmm.
His son wrote that, quote, the most principal trait in my father's character was without a doubt the splendid truthfulness of his nature.
A man of integrity.
Hmm.
Mm.
And his brother said that he was a man of, quote, rare modesty.
Brilliant but modest.
Yes. But we also have a reference from one of Rudolph's students who refers to him as, quote, that old grouch. Yeah. Although I have to say, I'm not really sure when that was written. So it could have been after he got his painful war wound.
And also, the student could be a disgruntled guy.
Yeah.
Once one disgruntled student does not a reputation make.
Yes, that's true. Yeah. But I
Yes.
was like, later in his life, he did have a bit to be grumpy about. He's got this painful war wound. He's getting irritated by Tate's misconceptions, and he's
Yes.
a
He's
single
lost his
father of 6
wife.
kids. Yeah.
Yes. He has earned his, if he was grumpy, then he earned it. He earned
Yeah.
it. He
Yeah.
earned the right to be
If he was a
grumpy.
bit short with you, it's like maybe he just didn't have the time. He didn't have the time to
Yeah,
deal with you.
absolutely.
In 1886, Rudolph got married to his second wife, Sophie
Mm.
Sack, and has one
Okay.
more son with her. However, 2 years later, in 1888, Rudolph passes away at the age of 66 of unknown causes.
Oh, wow. Oh, but he did marry so late, huh? At 60, he marries at 64 to his second
Mm-hmm.
wife and has
Yeah.
a son at the age of 64. Mm.
And again, it's just like we don't have the details. I tried looking up who Sophie Sack was, and like her background came up empty. Tried looking into what happened to Rudolph. Why did he pass away? Don't know. No one seems to know. So there's just really this dearth of information about him personally.
But he came up with the first two law of thermodynamics and that is such a huge deal.
Yeah.
Plus, he's sort of starting to toy with the idea of how much can a molecule actually move, how much can the path length really be,
Yes.
considering the amount of interference that it's going to face from other molecules who are also jostling around in the same place. So he has these multiple excellent concepts. So then people are so focused on what he left in terms of scientific discovery that I can well see, especially with his own modesty and integrity, he's like, oh, let the light shine on the work and not on my own personal life.
Well, there was actually a really good quote about this from a book called Great Physicists from Galileo to Hawking by William H. Kruper. And he wrote about Rudolf Clausius, quote, this is an impressive story, but
Hmm.
as a story, it's disappointing simply because we still do not know the main character. Most of us would consider it a great misfortune if we knew no more about Cezanne, Flaubert, and Wagner, say, than what they put on canvas or paper or in a musical score.
Hmm.
Clausius, their contemporary and equal as a creative genius, has been taken from us as a human being in this way. We should mourn the loss.
Oh, wow. That's a good thought. Like, yeah, you need to know who the person is behind that discovery.
Yeah.
We know him more one dimensionally then. That's
Yeah.
because you're only knowing him through the dimension of his work in physics and thermodynamics.
Yeah. And it's like, can you imagine some great artists like Pablo Picasso or Beethoven, and all you had of them was their artwork or their music,
That's
and
right.
you knew nothing about them as a person or what inspired them or anything like
Yeah.
that?
Yeah, that would be a great loss to not understand where the work originated from.
Yeah. Yeah. So that is part 2 of our inadvertent, totally not planned series on thermodynamics and
Oh, but
physics.
this is
Yeah.
fascinating, absolutely fascinating. And you're doing such a good job of leading me through the science. It's like I can see the building blocks all stacking up to create what we know today.
I
So
hope so. I
excellent.
hope I'm getting it right. People out there are very, very good about letting me know when I made a mistake, and I appreciate that.
Absolutely. Yeah. Any mistakes in the science, any mistakes in the pronunciations, we welcome all
Yeah,
corrections.
we're here to learn too. So let us
Yes.
know. It's a
Yes.
two-woman team here. We don't have a big team, so you're our team.
I'm learning a lot. I'm learning a lot. So I appreciate this opportunity to be here.
Awesome. Great. Well, we will see you next time in part 3, which is the one that Arun actually wanted me to do and started this whole thing off with.
And that will be the grand finale episode for the year 2025.
Right. Yeah, we're at the end, almost at the end.
You'll end the year with the finale for this trilogy.
It's very fitting. It's fitting in every way.
It's beautifully planned out.
Yeah.
Unplanned,
Totally
unplanned.
planned.
Yeah.
Totally planned.
Yeah.
Yeah.
Unplanned, but sitting out so beautifully.
Thanks for listening. If you have a suggestion for a story we should cover or thoughts you want to share about an episode, reach out to us at smarttpodcast.com. You can follow us on Instagram, TikTok, and Blue Sky at Smart Tea Podcast and listen to us on Spotify, Apple Podcasts, YouTube, or wherever you get your podcasts. And leave us a rating or comment. It helps us grow. New episodes are released every other Wednesday. See you next time.